were in an integral. What one of them does not need trig sub? What one of them in an integral with du, no 1 over, just an integral of an expression d, what one of them could you solve? No 1 over. Which one could you solve?
The one on the bottom?
Nope.
No.
I'm going to go with the square, the plus, the one with the plus.
One with the plus? Nope.
The one.
Why should you be able to solve this first one?
Oh, because you can have x squared minus 9.
Not arc sign, because it's just going to be the integral.
Because then you would get like, you could separate it.
You can separate it inside the rock.
Why did I change the a to an r?
It's
Is it? No.
Pi.
It is.
Oh, wait, it's a circle.
It's a circle, yeah. There's something.
No, it's a circle.
It's a circle.
Circle.
That was, yes, that was 7th grade.
1/2 pi r squared. What was the other? 1/2 pi r squared. Question: have we ever added this into our forever cards, even though I talked about it a million times? Does anybody have their forever cards?
No.
The funny thing is, your forever cards from last year have it in forever card number 1, or the basic graphs. Yeah, they do.
We have the unit circle, but not the circle.
Not forever card 1, sorry, forever card, the basic graphs. Here, look.
I do.
It is, though, I promise.
You promise, Missy?
Well, I don't promise, but I think. I believe.
Project it and just stay with you.
Oh no!
You're gonna have to pay for the people.
Is it logistic and tangent inverse instead? It's not.
Misty, your belief is wrong.
What's the 30-second?
Yes. Yes.
What's the...
I got the 30-second card.
It's the integral of...
There you go. Now it's there. Using the forever card number 2 at some point in time, because not only do you need to know logistic growth and tangent inverse, you also need to, and you needed to last year, know that constant squared minus x squared is a half circle. And how can we find the area of a half circle? 1/2 pi r squared. Dun, 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 dun. Okay, fine. There it is. Yay, it's there. You're welcome. All right, coming back. So, we can do the first one, but guess what? We can't do the second one, and we can't do the third one. Ooh.
Oh, our calculators can.
Indefinitely?
Yes.
Indefinitely?
With the right calculator.
With the right calculator, yes. Okay, so what do you do? Ready? Go. Here's like your first problem on your worksheet, right? There's a square root, which means we can't use arctan. Here's a problem like the first one on your worksheet. There's a square root, and it's not arctan, there's not a minus. Sorry, it's not arc sign. So what do? You say, you know what? Hold on. Pause. Shush. Back. You say, I think this was a side in a right triangle. Because the Pythagorean has squares and square roots.
Yeah.
So then if I was to go ahead and make 2x here and 1 here, question, wouldn't this be the square root of 4x squared plus 1? Ooh.
Yes.
Now, hold on. Trig sub. There's no sub there to begin with. Sorry, there's no trig there to begin with, and we want to get trig in. Well, how do we get trig in? Question, what can we say is equal or equivalent to the square root of 4x squared plus 1?
The tangent.
The cosine.
Not cosine, though.
But that's what you wrote.
You said it nicer. Not the sign.
Cosine. Cotangent.
Arctangent.
Secant.
Secant.
that makes sense.
Ew, but who wants to put in divided by secant? So why don't you think about what is cosine? What is cosine?
1 over secant. 1 over.
You got it.
Okay, does that make sense?
Math.
So could I change this to be the integral of cosine of theta dx?
Yes.
Now, why is that a problem?
It's a
Because you don't know theta.
Yeah.
I'll say that.
So how do I substitute for dx
Convert,
in terms of theta?
Convert,
I can't convert.
Okay, well, you solve for theta.
You saw it.
Hold on, pause.
I'm confused on the whole triangle.
Okay, I'm showing you how it works, so I haven't exactly taught you what to do. But what I did say is, hey, guess what? If we were to make this side 2x and that side 1, Pythagorean theorem would say a squared plus b squared is c squared, so it's the square root of a squared plus b squared. And then I said, hey, guess what? So I was showing you the discovery. That matches. Trig sub. All right, let's write a trig expression that has what we want in it so we can put in the integral. But the dx and the theta don't match. So Corey, what do you think?
Well, I just wondering, could you take in cosine, change it from polar parametric and parametric to linear? I know it's longer than.
The dilemma is if we were to try to do that, we would end up with the same dilemma that we can't solve. We want the trig in there because it'll make it possible. If we can convert with trig, simpler and easier than with algebraic expressions usually. Because of trig properties, t-proofs, and fun stuff like that. Question. I need a dx. Come on, what do we always do when we need to substitute differentials?
Subs.
Take a derivative. Right? U prime, u du. We have the u, but we also need the du. What haven't we done yet? The derivative. Now, it's not just a u, it's a cosine theta, but whatever. Can't we take the derivative and say that's going to end up being negative sine of theta d theta?
Yes.
Right? And couldn't I take the...
No.
Do I want to take that derivative?
No.
Question.
Or, no, wait, isn't it just on the thing matrix?
Wouldn't I have to... But I'd have to solve for this whole
Or
function.
you suffer dx.
Pause. What's a lot easier than taking a derivative of this?
Integrated. Third tangent.
Find the derivative of that. Doesn't this also have a d theta and dx?
Yeah, so you substitute.
But I'm using something easier.
Thank you.
So I can go ahead and say, oh, sweet, okay, so secant squared of theta d theta is equal to 2 dx. Thanks, Kim. Now pause. Why didn't I just use that? Well, that's going to be gross. What's better? Because I don't have anything else to get rid of. I got rid of everything with x's except for dx. I want something simple. Oh, 2x over 1, the tangent is simple. Take the derivative of tangent theta, secant squared theta d theta. Or theta. It'd technically be d theta dx equals 2, and you move the dx to the other side. So what do we do now?
We'll over the
Move over the 2 and say, no big deal, we know what dx is. Awesome! So now we can say this is the exact same thing as the integral of,
oh, the answer.
pull out the 1/2, then we have cosine theta times secant squared theta d theta. Because I'm just substituting for this guy.
Which is secant.
Does that make sense? So I'm plugging in.
No, secant cotangent.
Secant times cosine, one of those will cancel. Won't I just have 1/2 the integral of secant of theta? Oh, if only we knew how to integrate that.
Oh, man.
Oh, yeah.
Absolutely. Oh, no, it's
Positive elements.
Secant plus tangent.
What's wrong? No, that's okay. What's that?
So you have the, but you change the cosine and you use the tangent instead. Why do you still?
Okay, because we were going to go find dx, but then when we started to take that derivative, it was easy, but this derivative, we were like, ugh, gross. So what I said was, hey, is there some other theta x expression we could write down that would be a lot easier to derive? So we needed this one, because we needed to get rid of 1 over square root of 4x squared plus 1, but we didn't have to use him for dx. We could use any expression, sine, cosine. Tangent would be the easiest, though, to derive, and to figure out how d theta and dx are related, and then plug in. Oh, I'm stuck. Wait, I'm done. No. Why? I need it in terms of x. I'm stuck. No, you're not. You have a triangle with opposites and adjacents and hypotenuses. And so who is secant? Sha. Hypotenuse over adjacent or cosine flip. That's boring. Square root of 4x squared plus 1. Hypotenuse over adjacent. Plus tangent.
2x.
We already know him. That's 2x. That was the original expression. Why, yes, indeed it was. Dun-dun-dun-dun. Crazy, huh? We use the trig to be able to consider this integral differently. Whenever you have something that could have come out of a Pythagorean theorem, an a squared, a b squared, a c squared minus an a squared, just maybe there are different sides that we plug in. So what was the first thing I did before we go to the example?
Rewrite.
First thing I did was realize I can't do it as it is. Then I rewrote, but I looked at this and said, hey, I think some of these are sides of a right triangle. How did I know opposite and adjacent? Why not hypotenuse?
And looking over anything? Because it was a square root. Oh my goodness.
Hold on.
You made it easier.
My head hurts.
Oh no, I don't want that. No.
Could you
Okay. How did I look at that expression and know? How did I know that I wanted to put this as the hypotenuse and not as the opposite or the adjacent?
Is this something added or something?
Added. Pythagorean theorem, a squared plus b squared is c squared. C has a plus in the a squared plus b squared. So I could go ahead and usually we put the variable one over here opposite. It's just easier because then you get to use tangent instead of cotangent. Well, usually we put the variable one here and the constant one here. What if I was to give you something like instead,
That's the B, not the C.
it needs to be a leg, not a hypotenuse, right?
Yeah.
What is the hypotenuse?
A.
Has to be A. Has to be A. Then we could still make that guy U. We could do a squared minus u squared. Technically, just from the geometry, we could switch it up, and it would still be right. But one of them will be simpler than the other. And it kind of depends on whether you have a 1 over that, or whether you have, wait, 1 over that. Can I do something with 1 over that?
Yeah.
Why?
Rule.
Which rule is a squared minus u squared? Arc sine. Now what if it was u squared minus a squared alone? Arcsecant? No. Don't you need that extra u? Okay. So if this was not in a denominator, okay. We're going to see some more examples. Is there any other way this could show up? What I was just thinking. What am I stuck making the hypotenuse now then? Then we could go ahead and technically geometrically, even though one way is easier than the other, we could make that. Okay. Do you get the idea of how we're taking an expression and plugging it into a right triangle? But we need to kind of figure out, remember there's these ors, let's figure out if one way is easier than the other. Let's figure out if one way is easier than the other. Let's go find with the minus. Oh, well, we'll come back to that. We'll come back to that. Anything with a minus? Okay.
Technically,
This one has a minus.
Technically,
Isn't that arcsecant?
It's not arcsecant.
No, because it's squared.
You're squared.
If it was just an x.
Oh yeah, true.
If it was an x to the fourth, no. Yeah, if it was an x to the fourth, that'd be good. That's not.
It's x squared times a circle.
Times the circle in the denominator.
Or you can make it 1 over x squared and the other thing can be and so on, then you could do the other substitute x. Okay.
So, what do we think? Why am I going to put a 3 here?
Because it's 3 squared is not.
R squared minus, hypotenuse squared minus log squared. Yeah?
X.
So then this is going to be an x, and then this is going to be,
Square root of square.
are we okay?
Yep.
So we've chosen this one with a squared minus u squared in the denominator. Ooh, something extra, couldn't do arc sine.
I'm extra.
We decided to make the variable the opposite and the square root the adjacent. Let's see if that works. Okay, we have some stuff to substitute for, yeah? So what can we do? Can we do a 1 over? No. Can we do a 3 over? Oh, okay. So what would 3 over be? Hypotenuse over adjacent. So we could do secant. That could I multiply by 1/3. So what could I substitute that 1 over 9x squared to be? 1/3 secant. However, the dilemma is if I go ahead and do that, yes, we still have a dx, but what else do we still have? Is there anything I can do with that?
Yeah, you can make it, we do like x squared.
Can you solve for?
You can solve for opposite over hypotenuse.
You just square it.
Opposite over hypotenuse, we could do that.
Opposite.
Maybe hypotenuse over opposite, because I need the x in the denominator.
And then just square root.
Who is that? Hypotenuse over opposite. Cosecant, right?
Yeah, you could square both sides, or else for usual.
So couldn't I do? You guys agree? How did I know that? Well, I didn't want that weird square rooty thing anymore. I got rid of him, so I just wanted x's. Okay, fine. Take something with an x. I can't go tangent. It would get a square root. Can't use the adjacent at all, so I could use sine. It's going to end up being over sine, or 1 over sine, which is cosecant. Simplify, then I'd square it, because it was a 1 over x squared. So then couldn't I pull out, let's see, a 127? The integral of cosecant squared. Secant? Oh, struggle. What's still missing? Okay. Do you want to take a derivative of cosecant or secant with x's in denominators?
Neither.
Okay, so what's going to be easier?
Tangent or sine.
Not tangent, because I'm going to have to take the derivative of this guy. Oh, but sine looks nice. So if you want, you could kind of separate your work and say, hey, for dx, I need something easy. Sine equaling x over 3 or 1/3 x looks a lot nicer than taking the derivative of any of those yucky things with denominators. Because then I get cosine of theta d theta is equal to 1/3 dx multiplied by 3. There we go.
Cosine and secant will cancel.
Nice.
Whoa. What's the notation for derivatives? We can do sine theta and
Well, if you do it this way, technically it'd be implicit differentiation, take d dx of both sides, so it'd be cosine of theta times theta prime, or d theta dx, equals 1/3, then you move the dx.
So what do we do if we will be prime?
D theta dx.
Oh, so you'll take d
Oh, d dx of both sides. Because we need to do it in terms of x to get that dx. I guess technically you could do in terms of theta.
Because I'm just confused.
You could do d theta of both sides, because then you have cosine of theta equals 1/3 dx d theta. It works either way.
So, like, notation doesn't really matter? Because on this
We need a relationship between the differentials, so we're not really caring whether it was a d theta dx, to where x was the differential in the beginning, and theta was the dependent, or whether it's dx d theta. Either way, we can move them again.
Okay, I was just thinking, like, if you do one side, you do the other side.
So I'm assuming I'm putting notation.
Yeah, DDX both sides or DD theta.
Okay.
What do I have? Oh, DX. So in the 3 and the 27, that's 1/9. You guys already got there, right? And then you have the cosecant squared times the secant times the cosine. I already brought in the 3. The secant and the cosine cancel. Oh, Steve, how do I integrate cosecant squared?
Negative cotangent with your
It's negative
Square root
cosecant.
of 9.
Wait, I need it in terms of x. Go to your triangle. Cotangent. Choshikawa, adjacent over opposite, or the reciprocal of opposite over adjacent. Either way. You end up with negative x over 9 square root of 9 minus x. Because, just in case I lost needed there, I apologize. Because if you were to go ahead and say, wait, I need cotangent.
No, it's adjacent over hypotenuse, so.
Oh, I did it backwards.
Oh,
It was my bad, I was doing it too fast. Adjacent over opposite.
Oh.
I said it right and I wrote it wrong. Oh, you were just
Pens,
copying
kids.
me? That's cute.
I did that. Just kidding, I was writing pen, I hate pencil.
I wrote it wrong. Cotangent, adjacent over opposite. And have pencil. Negative. Dun, 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 dun. Dun, dun. How else would you get it? I don't know, you need trick stuff. Because trig, we can play with properties and identities and we can bring in some of our transforming skills that we haven't seen a lot, or needed a lot, but trig stuff, oh, they help so much. Okay, can we go back to the steps just a little bit, just in case you guys want to write down some steps?
Is the first one always the hypotenuse?
If it's subtracted,
If it's
because it's c squared minus leg squared equals other leg.
okay.
If that makes sense.
It's the page where you have all
Yeah.
of the different notations connected around.
Let's start here real quick. There are 2 pages that we skipped. One of them is just a general how, and just to make it nice and easy, if possible, sticking with sine and tangent and secant in like how you're setting up the triangle is nicest. Sticking with sine, tangent, secant when you're plugging in is nicest. This one we did end up doing cosecant. It ended up working. Not saying that you can't, but the general rule is you do like to stick with sine, tangent, secant. Set up triangles, and you guys, we kind of got a feel for that. Hypotenuses, legs, based on whether you see a squared plus b squared under a square root, or a squared minus b squared. Solving for x, and not just x, solving for the x expression. Like we solved for the square rooty thing because we needed to plug in. We solved for 1 over x squared, so you can be creative in that. Or you could just solve for x and then plug in. And then finding dx in terms of theta, meaning theta and d theta. And then go getting rid of everything with x's, get rid of the dx, and then say, all right, let's play with trig properties. Real quick, if it is definite, if you could, for a definite integral, change the function in terms of x to a function in terms of theta, the dx to a d theta, couldn't you just change the bounds to theta bounds and never have to go back to x?
Yeah.
Doesn't mean you have to. The same way as last year you guys were all arguing about whether or not to go to u bounds. I'm just saying you could.
Never.
Just saying you could.
I forgot how to do it.
But for that, would you have to, if you wanted to use theta bounds, would you use, what would you derive?
Well, you can use, I mean, you're going to have different expressions. You can use whichever one is more natural. Because whenever you plug in an x, you're going to get a value that you're then going to have to undo a trig to find the theta bounds. So if you like sine better, plug into the sine one and then do sine inverse or cosine better.
But so it can be either any you want from the triangle.
Yeah.
Wait, so theta bounds will be theta?
For our purposes, because all of calculus is movement. We don't go to degrees unless it's just for reference. With that, kiddos, can I show you really quickly an alternative? If we were to follow these directions exactly, solve for x exactly, couldn't I have, ready? Couldn't I have done the following? Couldn't I have started off not with secant, but started off instead with sine? Couldn't I have taken this sine, multiplied the 3, and said, hey, x equals 3 sine of theta? Couldn't I have plugged in 3 sine of theta and 3 sine of theta? Guess what that would have ended up changing to after using Pythagorean properties and other stuff? It would have eventually gotten here. What I was doing was showing you that, hey, you know how to work with sines and cosines and tangents. Like, we can actually get expressions that match instead of just solving for x and then having to transform. I went ahead and showed, hey, cool, let's use secant, and then we can just plug that in. But you could, if this is too confusing and creative, you could just say, hey, let's take the expression where I have an x and a number, sweet. Get the x alone, sweet. Plug it in everywhere, now use my trig skills to help me get an expression. That works too. That works too. Maybe I'll use that in the next example. But there is one more page, and I mean, this is what you're asking for. That does kind of say, hey, when given, you probably want to set up your triangle like this. So this is technically the easiest way to deal with each of these scenarios. You don't have to memorize these. You don't even technically have to write them down. But what they're saying is, if you're given this, you could automatically say, hey, let me put the u there, the constant there, the radical there, and then I can say that sine of theta is equal to u over a. AKA u is equal to sine, a sine theta. Then I can plug that into there and then play with the trig. But I don't know if you necessarily want to write down and memorize these.
No, not really.
It's more conceptual.
But it might be nice to get into the visual because I've just shown you guys using the right triangle because that's the way my brain likes to process it because I know how to work a right triangle. But for some of you, it might be nicer to have a formula and say, all right, fine. And remember, this is an aside. We're seeing how to do it, playing with it on a worksheet. Asking a few questions on Monday and then going from there.
We go follow with them. Using data.
I think I have one. Let me freeze the screen while people, really quickly while people are writing things down. Wow, that was not coming out well. Oh, wrong one. Yeah, I have them, Kyle. There we come. Won't be the next one, but it'll be the second one. Pause real quick. If you want all of it, take a quick picture. If you have it. If you want all of it, take a quick picture. Because we're going to go on to an example just because we're running out of time. Unless you don't have your phone. Just kidding. We'll give them a couple more moments.
There's more of a camera than a phone.
Mental picture.
Quick phones.
My gosh.
There's some guy, I forget who it is, I heard a podcast on like NPR, I don't remember when, who has basically been operating with a computer for the last like 20 years. Like before Google Glass. Like, not part of this, not really part, but he has this whole contraption that he puts on every day that has like a voice recorder and has like a, so he was able to operate, to remember conversations, he was able to recall, it had like headphones, it was, yeah, it's this whole podcast. To where he's making the argument for, is it really, I forget his name. And he has a name for it too. But his argument is, like he's a college, I think he's a professor or something. But his argument is, I should be allowed to use this because this is how I operate, this is a part of who I am. Like this isn't just for an unfair advantage, this is what I use every single day, this is who I am every single day. Like someone being able to wear a pair of glasses that aren't Google glasses, like that's a part of who you are and that's how you operate. He remembers like conversations with people, he's able to recall like face recognition in order to be like, oh, hey, it's this so-and-so who's coming up, and he's like, hey, so-and-so, like, hey, remember, this was going on. Oh, hey, how is this? Anyway, it's pretty cool. pretty crazy.
Wait, so it's technically aid more than use.
It's like a personal assistant that's always in use.
Yeah.
But he's making the argument it's a part of training. And so then he should be able to use it for anything that he might ever need to do. So that's interesting as far as like students and tests and learning and anyway, and where our world is going with things like Google Classes and
So without it, would he still be able to remember everything?
not to the same extent because the system's always reminding him. But then there's also like some argue like, are you ruining your own ability? Like if you ever this was taken away, like would you still be able to operate?
Because I guess it depends.
There's a lot of arguments. It's just interesting. All right. Woo! What's this one? 3 halves.
You can change it.
Make it something different.
Yeah.
Something
Yeah,
different.
make it something different. You can just separate it.
So, what if we were to use the idea, wait, it's plus, right? So I'm going to have x and I'm going to have 1. I can go ahead and do the 1 plus x squared. What if we do the whole idea of just solving for x? Saying this isn't maybe quite so easy to see, even though in my mind I can make an argument. But what if we were to do it where we just said, okay, fine, tan of theta is equal to x over 1, aka just x. So I came over here and said, hey, what if this, well, I could just do secant squared of theta, d theta is equal to dx, because I already have the easiest expression. Then I can go ahead and plug in and say, all right, fine, I don't know exactly what's going on, but I can say it's the same thing as, now we could play with it. This isn't the only, oh, sorry, theta. This isn't the only way of doing it, but this is what that table is that some of you just wrote down. Not only the picture, but also how just solve for
No,
x.
it's tangent plus 1 squared plus 1. Never mind, you multiply to
X is equal to tangent, so I plugged in. So tangent squared of theta plus 1. It's a different approach. So I'm not trying to make this look nice right away. I'm just saying whatever, get it in. Now play with it. Well, how do I play with it?
Never mind, it's not.
Oh, can't you take up the secant and then
Tangent
put
squared plus
it
1 is
Oh, no, I'm just
Yeah.
secant squared though, right?
Yeah.
Pythagorean property. That's the same thing as secant squared. Oh, that's nice.
Then you can
Hey, a square to the half power. Isn't a power to a power you multiply?
1 over secant.
So that's the same thing as
What over secant?
secant cubed.
Cosine?
Secant squared over secant cubed will be the same thing as 1 over secant.
Which is cosine.
Cosine.
Cosine, which is negative sign.
That just blew my mind.
Oh, no. Something so complicated, but I mean, it's so much easier. The secant squared is true.
Secant squared property.
Pythagorean property, 1 plus tangent squared is secant squared, or tangent squared plus 1 is secant squared. It's a Pythagorean. You could always make it sine squared over cosine squared, common denominator, sine squared plus cosine squared over cosine squared, 1 over cosine squared.
Cosine squared. Oh, it's actually what are you thinking?
I don't know.
Stop judging. Wait, it's a positive sign. You're going to make that mistake too. Careful. Integral of cosine is a positive sign. How do I solve? Look at it and say opposite over
X over square root.
Dun, 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 dun. Dun, dun.
Oh my god.
What's wrong? Did this make sense?
Yeah.
So then, did it make sense how I took tangent for x?
Why did you choose tangent?
In the big old table of properties, or even on the steps that we wrote,
Yeah.
it said one approach is that you could just take the simplest expression and solve for x. And then you could just say, I don't know what this thing is, but plug in x, now I just have trig, let's go, and play with it.
And then the secant and
Came from there. So I plugged in for dx. Does that make sense? Okay.
How come you were able to make it a square root instead of 3 halves when you did the triangle?
Oh, because I was showing you an alternate approach to trig sub is not to necessarily choose the trig function that gets rid of everything, but just take the simplest solve for x and say, okay, whatever, I have x stuff over there, let me just get rid of all the x stuff with trig. So I wasn't trying to make it match in this one. So one approach is, don't try to make it match, just get x real quick, as fast as you can with trig, get rid of the x and say, all right, I'll play with it in a trig way instead. The other way that you could have done it is that you could have made this x squared plus 1 times square root of x squared plus 1. Then you could have gone ahead and plugged in tangent there, and then you could have plugged in the square root using, I don't know, probably secant. And it would have been the exact same thing. So 2 different approaches. This approach, I wasn't trying to make it match. I was just saying solve for x and plug in. You could do that every time. You could have also tried to make it match by making it this to the 1 and this to the 1/2 or square root of, and then try to get functions that would take the place. Both ways work. Okay, there was a question or a request for a definite. Ew, gross. That could be in the integration table. So some engineer might be like, I don't want to solve it by hand. Gross, and go like look it up in this huge old table of stuff. That's all that's saying. There are huge books. Dr. Teague, I don't know if you guys remember him, he used to have this big book of integration tables that applied mathematicians like like engineers would have. If they ever needed to solve an integral, they would just start looking this big old book of tables for the right formula. And these are some formulas that we're looking into.
So we can just memorize that.
If you want to. I'm not going to make it an endeavor, but if you want to. But remember, these don't really show up on the AP.
Oh, what we're learning right now isn't on AP?
Number 10.
Oh,
Number 10 on Barron's had an integral that could only be solved with trig sub, but you could have thought about it. It was a conceptual and you never had to actually integrate it. So it could be useful, but it's not required. Okay, here's a definite one. What do you guys think?
It's the same thing.
Careful, x is the hypotenuse though, right? Where are we going to put the 3?
On the bottom.
Oh, not even 3, rad 3.
Yeah.
Because we need to take the square root of that guy. Do you guys want to do the solve for x thingy again?
Yeah.
Okay, so the easiest one would be I see x over rad 3, which would be secant. We're not even worrying about trying to make it match. We're like, forget it, just get x alone. So x equals rad 3 secant. So you can go ahead and plug in and say, all right, so x squared, so rad 3 secant. Same can eat dx, but no big deal. Take the derivative of who you have right here. That is dx. Yep. Struggle. Are these two the exact same?
Yeah. No.
What's missing?
Yeah.
No. So what could you do?
What is it? Plug those numbers into that and get it.
When x equals rad 3, you can plug in, solve, or you can just do it indefinitely and plug in the x's later. Does that make sense, Kyle? You can plug into x and use the unit circle and solve, or you can just get it in terms of x and then just take your x. Wait, pause! You might want to see this. Shared Google Drive. Handouts and assignments. I have the answers and solutions. AKA worked out calc chat wise. Bye guys, to the worksheet, yeah. Under handouts, assignments, trig sub, worksheet, solutions. Come under questions.